1/2 mv initial squared is going to equal mgh final. Yeah, Rem, do you want me to keep going? So my masses can cancel. Doesn't actually matter how big the truck is. 1/2 times, what's 90 in meters per second? 25 meters per second. 25 squared equals 9.8 height final. So 25 squared divided by 2 divided by 9.8. You should get a final height up the ramp of 31, vertically, 31.9 meters is the increase in elevation if you're able to ignore friction. Does that make sense? Okay. So then the second part says, if friction is taken into account, what's this going to do? Is it going to be bigger or smaller? It should be smaller, because you're going to have there's going to be a work term here that is not zero, that is going to be negative, because friction is going to drive heat energy out of the system. So this is the maximum possible value if you greased up that truck real good and it was able to ignore the friction of the rocks. A lot of Vaseline. Otherwise, it's going below 32 meters. Okay. That's 3 of the questions I assigned for homework yesterday. Comments, questions, concerns? Would anybody like me to go over anything else? Yeah, Dwayne? Number which? Number 13. In an electronics factory, small cabinets sliding down a 30-degree incline, a distance of 16 meters. Okay, there's the incline. There's the track. There's a track. We're told that this is 30 degrees. This is a 16-meter long ramp. Cabinets have a mass of 10 kilograms each. Calculate the speed each ramp would acquire if the incline were frictionless. So the key here is you need to use trig, Dwayne, to figure out what this distance is here. You're going to use, to figure out this, I'll call it h. No, I won't call it h because that's like hypotenuse. Call it x. We're going to use sine because that's the opposite side, that's the hypotenuse. The sine of 30 degrees is going to be equal to the opposite over the hypotenuse. So x is going to be 16 sine 30, which is that going to be 8? Is sine 30 a half? Is that one of those? Sine 30 is a half, which means x is 8. So that's that. So we're going to have energy initial plus work equals energy final. It's frictionless, so that's 0. Initially, well, presumably they're just being placed on the incline. This seems to be what it's suggesting. So you're just going to have potential energy to consider at the beginning. You're just going to have kinetic energy when it reaches the bottom of the incline. So mgh initial is going to equal 1/2 mv final squared. Masses can cancel. So we're going to get 9.8 times 8 times 2 square rooted is going to be the final velocity of those cabinets. 2 times 9.8 times 8 square rooted. I got a final velocity of 12.5 meters per second. And then to figure out the kinetic energy a cabinet would have under the circumstances, square it, multiply it by the mass, divide by 2. But that's how fast those cabinets are going to hit the bottom of the incline. And they're dropping 8 meters, so that is not an insignificant fall. Comments, questions, concerns? Okay, is there anything else anyone would like me to look at before we do today's lesson? Okay, hearing nothing, what I would like you to do is I'd like you to flip ahead until you can find this page. Thermal energy. Okay, here we go. Okay, so thermal energy. We've looked at kinetic, we've looked at gravitational potential, we've looked at spring potential. Now let's look at thermal energy. Thermal energy is arguably the next biggest thing you're going to consider as far as energy you experience in your life. The kinetic molecular theory, something that used to be part of the Science 10 curriculum. I believe now it's moved down into middle school. It's the idea that all matter is made up of tiny particles, atoms or larger molecules, and that these particles are always moving, except when. Does anyone know when these particles stop moving? Alana, was that a hand? No. When does all particle motion stop, sire? At absolute zero. Which is 0 degrees in a temperature scale called Kelvin. And if you convert Kelvin to degrees Celsius, it's a really nice conversion. 0 degrees Kelvin is negative 273 degrees Celsius. Basically, degrees Kelvin is equal to Celsius plus, no, that's going to be, oh no, let's do it this way. Kelvin minus, nope. So that should be minus 273 degrees. Nope, that's the wrong way, plus. Degrees Kelvin is equal to degrees Celsius plus 273 degrees. So 0 Kelvin is absolute zero. Nothing, there's zero motion, zero atomic motion at that temperature. Water freezes at 0 degrees Celsius. So water freezes, or would be ice, up till 273 degrees Kelvin. Water boils at 100 degrees Celsius, so that would be 373 degrees Kelvin. It's a straight conversion. Kelvin is degrees Celsius plus 273. It's not like the ridiculous Fahrenheit scale that we look at. So the kinetic molecular theory states that particles are always going to move. In solids, liquids, and gases, these things move in different ways. What are the 3 ways a particle can move? What are the 3 ways you can move? Think about how you move. What are the ways you can do that? Okay, we call that translational motion. So you can move translationally. A translational is not just left to right or side to side, as Brad said. It's also up and down. Up, down, frontwards, backwards. These are all of the ways that you can move translationally. And only some kinds of particles in certain states of matter can move this way. What kinds of particles or what kinds of states of matter allow their particles to move translationally? Liquids. Liquids can flow on their own, kind of spontaneously, if given the correct amount of space. What other states of matter can do this? Gases. Gas and liquids are allowed to move translationally spontaneously. They will do this on their own. Solid states of matter do not. It would be weird if your desk just moved. Left, right, up, down, forwards, backwards, on its own with no outside interference. That would be odd. You should be concerned. But but liquids and gases can do this. How else can you move? Sire. You can spin. We call that rotational. This is spinning. And there's all sorts of ways that you can spin. You can spin like this. If you were at the top of the stairs and someone pushed you down, you could spin head over foot. There's all sorts of ways you can spin, different axes you can spin on. If you find yourself in kind of an unfortunate situation, there's all sorts of ways we can make you spin. Amusement park rides are dedicated to this spinning. How else can you move? You can move translationally. You can move spinning. Rotationally, how else can you move? Sorry? Not necessarily. You could apply it to yourself. These are all things you can make yourself do. Sire. Yes. And now this isn't something you guys do all that often, but molecules, atoms do this on their own. You can, as far as you can think of it, you can think of it like stretching. Without moving, you could reach your body to grab something that isn't immediately available to you. I can't reach my USB hub right there, but I can, without moving all of my body forward, I can reach forward, I can stretch a little bit, and there it is. Now I can reach it. I haven't left my desk, my chair hasn't moved, but I've reached out and I've grabbed the thing. Molecules do this all the time, except they don't do it with any sort of intentionality like that. They're just kind of springing back and forth. So there's vibrational energy. You can think of it like a shaking. Translational is restricted to gases and solids. Gases and solids can do all of these three. In fact, they do all the time. These two are what solids are doing. If you were able to observe the desk, for example, under an electron microscope, you would see the molecules in the desk vibrating just a little bit. Perhaps they're spinning, changing their orientation. Probably not, but they could. There's ways that we could make that happen. And each one of these types of motion is considered a type of kinetic energy. We've only looked at translational kinetic energy, but there's kinetic energy of motion. There's kinetic energy inherent in the vibrations of things. And if we combine all of these things together, what we do is we lump them up and we say, okay, well, the total combined energy that the particles have in all three of these ways, we define to be their thermal energy. We lump them all up, that's thermal energy. So potential energy also, and there is chemical potential energy inside the bonds between the molecules. So there's all sorts of energy packed into an object that otherwise doesn't look like it's moving. So thermal energy we define to be the total energy, all Ke and Pe of all the molecules in an object. Calculating this can be hard to do, really hard to do. But that is the definition of thermal energy. Heat. Heat is related to thermal energy, and this is something that we can measure a whole lot more effectively. Thermometers can do this, thermal imaging can do this. We have ways to measure the heat, because heat is just like you radiate the heat that you possess, assuming that your heat is less than the heat around you. If the heat around you is greater, then heat's going to flow into you. And if you are the same temperature as your surroundings, the heat's not going to go anywhere. So we have ways we can measure the heat values of these objects. How we define heat, well, how we'll measure heat is the transfer of thermal energy from one object to another. So I have some red, I have some blue, let's use these. So let's say I have an object here. This object is red, and it is right up against this object over here, which is blue. Red and blue are the universal colors for what? Hot and cold. So this is a hot object. If you're colorblind, this is a cold object. What does heat do? It's the transfer of thermal energy. Which way does thermal energy always flow? To the colder object. Heat always flows out of hot into cold. Because what is cold? Cold is just a lack of thermal. Cold in itself cannot be defined. It is just the lack of something else. Like darkness. You can't define darkness. Darkness is just the lack of presence of light. Cold is just the lack of presence of thermal energy. And so energy is going to flow always from areas of high energy to areas of low energy. And energy will flow until both objects have the same thermal energy. What do we call it when both objects have the same thermal energy, do you think? Using physicsy words we've looked at before. What is a way to make this thing sound more complicated than it is? Yeah, we're going to use that word equilibrium. What kind of equilibrium? What kind of equilibrium have we reached if they have the same amount of thermal energy? Thank you, whoever was brave enough to say it. Energy flows until both objects have the same thermal energy. We call this thermal equilibrium. A really easy way to say that two objects are at thermal equilibrium is that those two objects have the same temperature. We still have not defined what temperature is. Thermal energy is the total energy of all the molecules in an object. Heat is the transferring of thermal energy. What is temperature? We need a definition for this guy too. Temperature does a few things with this value. Thermal was all of the possible kinetic and potential. What temperature does is it takes the blank, leave some space there, kinetic energy of the particles in an object. So temperature drops out the potential energy. We don't care about potential energy if we're concerned with the temperature of an object. There is a mathy way that temperature gets calculated. Does anyone want to take a guess at what goes into that blank? I'll give you an example and let's see if we can pull out the answer. Let's take a look at this example here. Which has more thermal energy, a lit match, a lighted match, or an iceberg? What does your gut tell you? Let's look at the definitions here. The thermal energy is the total energy of all the molecules in an object. What does your gut tell you? Here's your iceberg. For those of you who don't know what an iceberg is, there's some water. Iceberg is a giant block of ice, and that giant block of ice actually is bigger underwater than it is above the water. Have a great day. Which is what sunk the Titanic, for those of you who care about old ships. Or you have a teensy lit match. There's your lit match. Which of those has the larger thermal energy? Looking at our definition for thermal energy. Thermal energy is the total KE of all the molecules in an object. So thermal energy is going to be dictated by how many molecules you have in the object. Which one has more molecules? The iceberg. By an order of billions, probably. An iceberg is a massive object. You're going to have tons of particles here. If you add up all the energy of all those individual particles, of course there's going to be more thermal energy available in that iceberg. So this thing has way more, substantially more. Substantially more particles. LES equals more thermal energy. If I asked you for temperature, though, which one's going to be a higher temperature? The block of ice or the lit match? The match. How? I mean, part of it is the fact that we're looking at, we're looking at less available energy. We're ignoring the potential energy. We're looking just at the kinetic energy of the particles, and you're saying that the temperature of the match is higher. You've experienced this. You felt it. It's hot. If it's hot, it means it has a higher heat than you do, and so the thermal energy flows from it to you. What can you do mathematically to get a higher value from a smaller number of things? There's less particles here. We're measuring less about them. What can we do? So it has a lower temp. Nope. What is the mathematical operation you're doing if you're dividing by something? Here, in this case. You're looking at the number of particles and you're dividing by something. Or you're looking at the kinetic energy of a bunch of particles and you're dividing by something. What would it make sense to divide by? Let me do an example for you. Here's what I mean. Let's say, we're cool with the fact that this is colder. Okay? So any individual particle here is probably going to have less energy than any individual particle here, right? Okay. So let's say that each one of these particles has an energy value. I'll make it easy for myself. Let's say they have energy values of 1. Every single particle has an energy value of 1. If you have 1 billion particles in an iceberg, how much thermal energy is available? Well, if each one has 1, now all of a sudden there is 1 billion joules of thermal energy here. The individual particles in a match are going to have higher energy. Maybe this one is 10 each, 10, 10, 10. Maybe there's not 1 billion, maybe there's 100. If I'm adding 10 100s together, what am I going to get? What is 10 100ths? It's 1,000. Thank you. So there's 1,000 joules of thermal energy here, and yet you know this is hotter. What could we divide both of these by to get something that makes sense to give us a value for temperature? What if I divided each of these by the number of particles that were present? That's something we could do. It's the same operation to both. So I'm going to divide this by 1 billion, and we're going to go back down to 1. I'm going to divide this, though, by 100, and we're going to go up to 10. We can say, oh, okay, cool, look. The temperature here is 10 joules, perhaps. The temperature here is 1. What did I do? By dividing by the number of particles, what mathematical operation have I just done? I found the average. The temperature is defined to be the average kinetic energy of all the particles in an object. And so that's why you can have smaller objects that have massively higher temperatures than objects that have much larger thermal energies available to them. So that is thermal energy, heat energy, and temperature. That's how these are related. Thermal is the total energy of every kind available to an object. Heat is the transfer of thermal energy from a high thermal to a low thermal. And temperature is the average kinetic energy of all of the particles in an object. Another question for you. If I was going to heat two objects, there should be an S there, a piece of metal and a pot of water, which would you expect to heat up faster? You've done this before, I would think. Which one's going to heat up faster? Sire. Saw that hand. Let's say you have the same amount of each. You have a 10 kilogram slab of metal and a 10 liter jug of water, because 10 liters of water is, every liter of water is a kilogram. So you have the same amount of each. Which one's going to take longer to heat? Which will heat up faster? The metal. The metal will always heat up faster. Why is that? Sorry? It more readily accepts energy. We have a concept for that. Conductivity. Metal is more conductive. Therefore, it will heat up faster. Water is less conductive, so it's going to heat up slower. There's another property at work here that I am going to talk about here next. I didn't have time to set up some demos because there's some demos I want to do, so we'll do them on Monday. Flip ahead 2 pages. Find me this page here. We'll do the in-between pages on Monday. And we'll jump to this. If we heat two objects at the same rate, they will not always increase in temperature at the same rate. This is because some materials are better conductors of thermal energy, as Sire just stated. We call this property the specific heat capacity of a material. The better a thermal conductor an object is, the lower the specific heat capacity will be. So specific heat capacity, I need to head, is the amount of energy in joules required to raise the temperature, I'll abbreviate it as the temp, of 1 kg of a substance (1 degree Celsius or 1 degree Kelvin. It's a very specific way of looking at something. No pun intended. The amount of energy in joules required to raise the temperature of 1 kilogram of a substance 1 degree Celsius or 1 degree Kelvin. This, I'll throw out where we'll throw it. We'll throw it here on this underneath. The smaller the value, the better the conductor. So let's look at this. I'm going to go to the left here. Let's look at this for a second. Let's look at the units and see if we can figure out the formula for this. Specific heat capacity is the amount of energy in joules required to raise the temperature of 1 kilogram of a substance 1 degree Celsius. So a way to look at this is it's the joules of energy per kilogram degree Celsius. The amount of energy, joules, required per kilogram per degree. And so we can take these units and we can go ahead and we can kind of reverse engineer what the formula is going to be to calculate this thing. So J is joules. Joules is energy, and in this particular case, what kind of energy are we talking about? I mean, we haven't really been specific, but we're probably talking about what kind of energy? Today's lesson's entitled what? Thermal energy. But nowhere in the formula does it actually specify that it has to be thermal energy, which leads itself to some ridiculous things. This could be kinetic energy. Yes, Henry. Say that louder. Who said that? Sire, was that you? Say it louder. Slapping a chicken until it cooks is exactly what I'm referencing. You can, because slapping an object heats it up. If you've never been slapped, go slap yourself. Just right across the face. Your face will heat up. You can slap a chicken until it's cooked. Unfortunately, Sire, have you seen the videos on YouTube about this? Yeah. The chickens disintegrate before they're successfully able to raise the temperature. I'll show you the video today. Actually, yeah, we'll end class this way. I'll show you the video today. You know what? Yeah, I'll show you to you. So thermal energy is in joules divided by kilograms. That's a mass. Degrees Celsius is a change in temperature, big T. And so what we get here is we have to now give this a name. Specific heat capacity needs a letter to represent it. And so what we do is we say, well, this is a capacity, let's call it C. Let's forget about the fact that we're talking about thermal. Well, we're not forgetting about the fact that we're calling it thermal energy. Let's have a very specific value, a letter for thermal energy. We're going to remove thermal E and we're going to call it Q. And so what we get here is that these values, specific heat capacity, is given C is going to equal Q, the thermal energy, divided by the mass of the object times the change in temperature. Now, while you're writing that down, let's see if I can find the slapping the chicken video. Okay, here we go.
Poor chicken.
Okay, so he's referencing. So I have not actually seen this newest video. He's referencing a video that he filmed a couple years ago. Is the one that I showed last semester, where the rig does get absolutely demolished while the chicken it slaps the chicken and heats it up. So this thing's gone up. I mean, where were we at? I lost it. Okay, so that 118 degrees is actually like rare on the steak scale. A rare steak is what you cook it to that. So they've actually managed to get to a rare chicken just by slapping the thing.
Interruption before the end of the day for an important announcement. This week we ran literacy and numeracy graduation assessments for students in grade 10 and grade 12. These assessments are required for graduation and many students have missed their assessment. If you have missed your literacy 12, literacy 10, or numeracy 10 grad assessments, you will have one opportunity to complete them next week on Wednesday The final opportunity to complete literacy or numeracy assessments is Wednesday at 8 a.m. in the Learning Commons of next week. If you have questions about this, please connect with Mr. Schroeder in the office.
Okay, this is where I'll pause. We'll finish it on Monday. Have yourself a great weekend. We'll see you later. The bell will go by the time you get to the door. At least it should. You can go.
Yeah, bro.
See you later. Yes. Yes, we are.
It just occurred to me that a photon is a particle.
Sort of.
At absolute zero, particles have no motion.
Yeah, but a photon has no mass, so is it a particle?
It's a fundamental particle. Of course it's not.
It's massless.
So a particle is a part of that.
Well, if it has no mass, can it be a thing?
It has no mass, but how does it generate a field? How is it a thing?
It doesn't generate a field. It just is. It is just energy. Because it's also a wave.
So it's energy.
Yeah.
It's a wave. Well, I guess waves are energy. And then you've got a photon's not a particle at all.
It has no mass. So if it has no mass, it can't have matter. If it has no matter, then can it be a particle?
Why is it on the same scale then? It's on the I can't remember. It's called the periodic table, as I would call it, of course.
It's a great question. Fundamental particles.
It's on the same chart as like bosons.
A fundamental particle is defined to be the smallest indivisible building block of the universe. That doesn't necessarily mean it's matter. So you have the different kinds of quarks, yeah, photons there, gluons there, bosons are there. The Higgs boson, also not a particle, but a thing.
I thought that, never mind, that's the Higgs effect.
Well, that is the Higgs field. Yeah.
That's the...
Photons carry electromagnetic force. Gluons carry the strong nuclear force. W and Z bosons carry the weak nuclear force, but are they particles? They don't have mass. Yep. They are massless particles that travel at the speed of light.
So I'm just going to take that at face value and just accept your suggestion that absolute zero will not stop their motion.
Correct.
Okay.
There's other things you can do to stop their motion, but temperature isn't one. Because we actually use lasers to bring things to absolute zero.
I have heard of it. That's how we make super solids now.
Yeah, you too, man. Sorry?
We made a super solid just recently, right?
Was it a super solid? I don't remember what it was.
They actually... I read the headlines. I never read too far into it. I feel like if I did, I would understand it. But there was the matterification, turning light into a tangible substance. But I don't really
That
know.
sounds bizarre.
Yeah, I don't know how reliable that is.
Hey, man. You've done more reading on this, obviously, than I have.
On Monday morning.
Yep.
I'm in here first block.
Yeah, and your kids are writing. Yeah, you mentioned you saying that.
Nice open room.
Sounds good.
Is it okay with you if I put a sign on the window?
Yeah,
On the door?
usually I just grab a whiteboard pen and just write on it.
I already printed one.
Okay.
But
That's
a
you
good
can
idea.
I just write. I drop the blinds and I just write on the window.
That's sweet.
But yes, if you have something to tape on there, by all means tape it. If you're taping, I would tape it on the inside just so no one gets rid of it. Okay, I need to mark some tests. Nope, it's over here. Oh, that was a bad throw. Good catch. Okay, let's go mark some dynamics tests. I dropped my car off an hour and a half ago or 2 hours ago and I haven't heard back, so I'm concerned.
Well, they called me and told me I could come earlier if I wanted to. So, I'm leaning more to the job was bigger than anticipated.
What was kind of happening?
Lights came on. Nothing changed in the car. Just, engine lights. In the RAV4 we have, the main one comes on, so all-wheel drive is traction control. Oh. Boom, the jack flew up. Have a good weekend, Kevin. You guys have a good weekend. Okay. Stop. Okay, when I get to it.
Okay.